Welcome to our Physics 211 Group Project 2, question number 1, by Ceiba, Cummings, Jacob Reierson, and Justice Peyton. For this project, we were tasked with finding the maximum height of two balls defined by mass 1 and mass 2 in a simplified version of Newton's cradle, with only two balls in a system including the strings and the earth and an elastic collision. The key physics concepts which were utilized in the solving process of this problem included the following laws of conservation of energy and momentum, elastic collisions, and energy. The following assumptions were defined. The kinetic and gravitational potential energies will not be converted to thermal or sound since there is no air resistance or friction. We will treat the energy and the momentum conserved in this scenario in regards to it being within the system of Earth. The strings attached to the balls are ideal, and thus the tension will remain uniform throughout the scenario. In this slide, we have provided a list of the known and unknown variables. Ultimately, our goal is to define the maximum height of which both of the balls will reach. Both of the balls start with an initial velocity of 0 meters per second, and then after release, m1 gains velocity until the collision with m2, where m1 and m2 are displaced, and each reach separate max heights of h1 and h2.
To better understand the problem, we created energy bar graphs to symbolize where energy is going. Note that the energy is fully conserved in our system of that of the left ball, the right ball, and the earth, and the energy does not convert to sound, thermal, or anything other than kinetic or gravitational potential energy based on our assumptions. Our bar graphs depict KE1 or kinetic energy 1 and GPE1 or gravitational potential energy 1 as the energies for the left ball and the others for the right ball. In the initial scenario, we have the left ball attached to a string that is theta degrees away from the resting string. This initial scenario depicts the left ball at its initial starting height, which is why it has a maximum amount of gravitational potential energy. The gravitational potential energy then converts into kinetic energy as the left ball is pulled downwards due to gravity, and just before the collision has fully converted into kinetic energy. Just note that realistically there'd be a very, very small amount of gravitational potential energy at this time since the two balls aren't intersecting with one another. After the collision, the kinetic energy is dispersed between the two balls. Since this is an elastic collision, the energy here is conserved. Note that the left ball doesn't always have more kinetic energy than the right. We simply decided to draw it like this for simplistic reasons. As the two balls move away from one another after the collision, the kinetic energy they received is then converted into gravitational potential energy. When the kinetic energy for both balls becomes 0, we have all energy put into the gravitational potential energy, which signifies that the balls have reached their maximum position post-collision.
The first step towards solving this question symbolically is to find the initial height of mass 1. To do this, we arbitrarily set the initial height of mass 2 to 0. This allows us to use trigonometry to calculate how much higher mass 1 is above mass 2, which is simply the length of the string minus the length of the string multiplied by cosine of theta. So now that we've determined the initial height of mass 1, we can calculate the total initial energy of the system, which again is the two balls, the string, and the earth. So first we need to note that the only form of energy initially is gravitational potential energy, because both masses are at rest, meaning there is no kinetic energy. Next, we can use the initial height we previously solved for to solve for the gravitational potential energy. The next step is to consider the collision. Since we know that energy is conserved in this system, we know that when mass 1 has a height of 0, the entirety of the original gravitational potential energy has transferred forms into kinetic energy. Additionally, we know that the initial kinetic energy of mass 2 is 0 since it is at rest, allowing us to ignore it. This also allows us to say the only initial kinetic energy in our system is from mass 1, which then allows us to set up the above equation and then plug in the variables we either know or have already solved for until we can isolate the velocity of mass 1 before the collision. The next step, now that we have solved for some specific variables, is to relate the energy and the momentum of the system, which will require some foresight into the problem. We know that energy is conserved because the question tells us that the collision is elastic. This means the kinetic energy before the collision is equal to the sum of the kinetic energy of both mass 1 and mass 2 after the collision, because there are no other forms of energy when the mass collides at the bottom of the pendulum when theta is equal to 0. And because this is true, we can set up the above equation and simplify the problem. The simplification is what requires some foresight because we want it to relate to the momentum so that we can use elimination later. We can now complete similar steps from the previous calculation, but now using momentum. We know the initial momentum before the collision is equal to the momentum of both mass 1 and mass 2 after the collision, which allows us to set up the above equation. The key here is that when we simplify the equation, we want it to formulate it into a similar manner of the energy equation. Now that we've related the energy and the momentum equations, we can use elimination and arithmetic to find the relationship between the velocities of both mass 1 and mass 2 after the collision. In using previous calculations, we will use substitution and plug the related velocities into their respective positions in the momentum equations. After plugging them in and isolating the velocity, we will determine each mass's final velocity after the collision in terms of variables that are known. The next step, which will be demonstrated on the next slide, is to determine the kinetic energy of each mass after the collision. And now that we have everything in terms of known variables, we can plug in the previous calculation for velocity and solve for the kinetic energy after the collision when the balls are at the bottom of the pendulum. The final step is to take the previous kinetic energies and set them equal to the final gravitational potential energy of each mass. This occurs when all of the kinetic energy transfers to gravitational potential energy, or another way to look at it is when the ball has reached its max height. Meaning, if we isolate h, we obtain our answer highlighted in orange.
As part of checking our work, I'll examine the units of our equation to see if we get the expected value, which should be meters. We can rewrite the equation we have for our height equations in terms of their labels. We can then simplify the labels, which will then tell us the SI unit of the result from our equation. Thankfully, the two equations simplify to meters as their SI unit, which is the expected unit for height. To better conceptualize our height equations, I'll be evaluating each height equation and seeing how each value within it affects the output. So on the left side of the slideshow, I will be showing several values and holding some of them constant, while one of them is variable. Here on the slideshow, the red graph is always going to be representing the left ball's final height versus the changing variable, and the blue graph will always represent the right ball's final height versus the changing variable. So using covariational reasoning, when we change the left ball's mass, we can see that increasing the mass of the left ball will overall increase the ending height of both balls. However, they begin to level off after a certain point. We can make further sense of this relationship by looking at how kinetic energy is affected more by velocity than mass. So more mass means more kinetic energy, and since kinetic energy is 1/2 mv squared, the right ball will contain more kinetic energy after impact, which increases the height of both the left and the right ball since more energy is present in the system. And notice how I said that velocity is the thing that matters more in this scenario, which is why we do not have as big of a jump. What would cause a really big change, though, is increasing the angle. Here I've graphed the two equations we have for the left and right ball's ending height, but I've made them dependent on the right ball's mass. Looking at this through a covariational perspective, we can see that as the right ball's mass increases, the ending height for the left ball initially increases but then flattens out. We can also see that the right ball's ending height approaches 0 but never quite reaches it. Realistically, a more massive ball being hit by a less massive ball probably won't make a more massive ball move very much, which is why we have the 1/x-like shape for the right ball's ending height. The 1/x shape is reinforced by the fact that energy and momentum do not just disappear. Even supermassive things will retain some momentum and energy from a collision. Now we'll look at the string length. Both heights of the balls increase as the string's length actually increases. This makes sense for a rather simple reason. Through a covariational lens, if we increase the length of the string, then we just scale the problem up more. This is evident in the equation we have, which is why we have a linear increase in height for both balls as the string's length increases. Realistically, a longer string length would just mean that you just start at a larger height, which means that more gravitational potential energy is present, and therefore more kinetic energy before impact. Notice that at a string length of 0, the ending height for both of the balls is 0. This special case, when thinking about it realistically, essentially states the left ball and the right ball are attached to the roof of what used to be the pendulum. This means that there's no collision that occurs at all since the balls start at the same position. Using our 0 position for gravitational potential energy, the resting height of the right ball is where gravitational potential energy is 0, which means that when the string length is 0, there's no energy to begin with in the system. Using covariational reasoning, we can see that increasing the angle up until a certain amount will result in the maximum height becoming larger. Since the graphs are in radians at about 3.14 or pi, the ending height for both of the balls will peak. This is because the starting angle for the left ball increases, which results in a higher starting position for the left ball. This means that there is more gravitational potential energy and therefore more kinetic energy prior to impact. At 180 degrees or at pi, the left ball is essentially parallel with the right ball, but at the very top of the pendulum. Naturally, this gives the left ball the most amount of time to build momentum from gravity pulling on it. Therefore, this, like string length, scales our problem equation up or down depending on the angle. Notice at an angle of 0, 2 pi, and 4 pi, and so forth, a special case states that the ending height is 0 for both balls. This is because at an angle of 2 pi or at 360 degrees, or at 0 degrees or 0 pi, the left ball starts on top of the right ball. Since the resting position of the right ball is where our gravitational potential energy is 0, there is no energy in the system at this angle, meaning that the ending heights will just be 0 since no collision occurs. Realistically, if you hang two balls, these two balls next to each other, and release, nothing's going to happen. There's no energy present and nothing that will cause a collision to move the balls. We will be testing our equations with one set of values. After calculating, I'll check the reasonability of the height we get of both the left and the right ball. Not only does it show us whether or not our equation is sound, but it allows us to visualize what exactly happens in this scenario. With a mass of 3 kilograms for the left ball and a mass of 0.05 kilograms for the right ball, as well as a string length of 1 meter and a release angle of 45 degrees, we get a final height of 0.274 meters for the left ball and a final height of 1.13 meters for the right ball. Looking back at our covariational reasoning in special cases, I can say this sounds reasonable. In reality, if you have a more massive ball hit a less massive ball, the less massive ball is going to react with quite a bit of movement. The more massive ball, however, not only translates momentum and energy into the less massive ball, but is still pulled down due to gravity, requiring more energy to recoil upwards in the other direction in reaction to the collision.
Similar questions can be seen used in the course's previous Week 9 homework assignment, Question 1 in the ball drop scenario from Lecture 19. Both of these questions include examples of energy transfer and conservation of momentum. The Week 9 homework problem also provided background on collision, and momentum was being conserved. In the ball drop scenario from Lecture 19, there is a relationship between kinetic and potential energy between the two balls at play. And this question also wanted us to find the maximum height reached.
As a final note, unit sets making is very important for us to check our work and understand what an equation provides for us. Graphing allows us to use covariational reasoning and see intricately how each value affects an equation. And a reflection on the team is the team worked quite well with another and divided the work pretty equally. And the reflection on the course is 211 was definitely a fun and unique experience with the group, and I've definitely enjoyed my time with them.